All right, the talk title is the non-invertible symmetries and 2D supersymmetric solitions. It's based on upcoming work collaborated with Qiang Jia, who is in the audience, and Zhihao Duan, and also Sanjay. So this talk is about the 2D solitions. So, oops. I think, okay. Anyway, it's about the 2D soliton. So let me first give some briefly, very rough introduction to this. Here, let's consider 2D theory of a real scalar field living on some interval, not interval, infinite on R, with a zero symmetry eta, which flip the sign of this scalar field. Then suppose we introduce such a potentials, which spontaneously breaks this zero symmetry, and we have two vacuum. One is the minus vacuum, and the other is a plus vacuum. Then the zero symmetry will flip these two vacuum in this way. Okay. We can introduce a total Hilbert space, which consists four parts, where the two signs, they enable the vacuum at the x to the minus infinity and also x to the plus infinities. And therefore, among them, this H plus plus and H minus minus, they are the Hilbert space of the particle excitations on a single vacuum, plus or minus. For example, it's something like that. It approaches a single vacuum at the infinity. And also the zero symmetry will map between these two Hilbert space. And there are also solitons or kinks connecting different vacuums in that way. For example, this is a solitons, and that is anti-solitons. And they belong to the Hilbert space H minus plus and H plus minus. And the Z2 symmetry, it will match between these two solitons. It is usually believed that the solitons as non-perturbative objects, they are very distinct from the particles, and they do not form any supersymmetry, any symmetry multiplets. So the question is that really true? This talk and our work is based on this background. If we consider the tricritical Ising model deformed by such Random operators, which I will introduce later, it will flow to the get phase in the IR with two vacuum. One is I, the other is W. Then the integrability analysis shows that there exists a triplet consisting of solitons, anti-solitons, and also a particle excitations on the W vacuum. And they have the same mass. It's a very old result. And recently, it is actually shown that these three states, they form a multiplet under the so-called non-invertible symmetry. So this story is basically based on those three papers in the last years. And so far, all the studies, I will review them later, of course. And so far, all the studies are focusing on the bosonic theory. Here, what we would like to do is to generalize the study to the fermionic case. There are several motivations. For example, of course, the fermion exists in nature, and also in 2D, compared to bosonic case, the fermionic case is much more subtle and less understood. And also one reason is due to supersymmetries. It's because we know in recent there are many developments in the generalized symmetry, but most of them they focus on non-supersymmetric series. And therefore, it is very interesting to try to combine the supersymmetry with the generalized symmetries. Right. And the talk contains the following things. The first, I will review the works done by those guys, and to describe this tricritical Ising model deformed by such operator, and to see how does the non-invertible symmetry constrain the representations of the solitons. And the second part, I will talk about fermionic generalizations. I will motivate that using the tricritical Ising model, which is also still tricritical Ising, which is also known to be a supersymmetric theory, and introduce the so-called superfusion category, and then present some results in the solitons in n=2 minimum model. All right. So let's start. So this is some introduction of general symmetry. In recent years, it was advocated that symmetry can be represented by such non-operators or non-defects. And if you have some local operators charged under this symmetry, then if you move this local operator across the symmetry, then this non-operator will implement some symmetry transformation on these local operators, depending on the representation. And this picture also holds for discrete symmetries and then also vast generalizations of symmetries. In this talk, we focus on the non-invertible one. That is a symmetry U, such that U fills U dagger is identity plus something else, right? And a consequence for this non-invertible symmetry is now if you have an operator phi, and if you move this phi, if you try to move this phi across these non-operators, then this non-operator, it will wrap this phi in this way. Then if you try to merge the middle double lines, and that will give you several channels, depends on these fusion rules. And usually this non-invertible symmetry can map a local operator to both to local or non-local operators, twisted by this L defect. A famous example is eigensymmetry in 2D. So where you have an identity C2 generator and there's a Cramer-Wagner duality of defect n. And this n is satisfied the fusion rule n squared is 1 plus eta, which is non-invertible. And this n, it will switch the order parameter or the order operator sigma to the disorder operator if you pass this sigma across this line. It will become a disorder operator mu attached to this eta line, the C2 line. So now let's move to the tricritical Ising model. There are 6 primaries, and their conformal weights are listed in this line. The non-invertible symmetry is also generated by 6 von Eden lines, where this I eta n, they are the Ising fusion they are the lines in the Ising fusion category we just introduced. And this W is also non-invertible, such that W squared is 1 plus W. And here we are trying to deform the series using a random operator phi 2, 1, this one. This deformation, usually it will break some of the symmetries. To see which one remains as a symmetry after the deformations, we can try to see, for example, we can pick an operator and to see whether this deformation is transparent to these null-operators. And it turns out that in this tricritical Ising model, only this W line is, this is only invariant under these W lines. And therefore, this IW, these 2 skies, they are preserved along the RG flow, which is, this symmetry is called the Fibonacci symmetries. And therefore, as I mentioned in the introduction, the IR gap phase has 2 vacuums. And these 2 vacuums, they must transform under some representation of the surviving symmetry. So it turns out that this Fibonacci symmetry is spontaneously broken in the IR, and one has such actions of the operator on the vacuum. For example, if you act the W symmetry on the W vacuum, that will produce 2 of them. There are 2 channels, it's I plus W. We'll draw the action of the symmetry like that. The vertical line is the vacuum, and the horizontal line is operators. So this diagram means if you act the W operators on the I vacuum, it will become the W vacuum. And this diagram means if you act the W operators on this W vacuum, it can map to the trivial vacuum, or it can map to the W vacuum. There are 2 channels. These 3 lines, they should satisfy the fusion rules on their junctions. And here, actually, we only consider the SSB phase, so that the vacuum, they are labeled in the same way as the symmetry operators. Then the Hilbert space are associated with the double vertical lines. The left is the vacuum at minus to infinity, and the right one is the vacuum at plus infinity. So we have such 4 sectors. Then to see how does the non-invertible symmetry give rise to the degeneracy of particle and solitons, let's begin with the KIW solitons. Is represented by these 2 ends, I and W. then the action of the W symmetry is this horizontal line. Then it will map this W to this WI. I say, for example, on the right part is W. On the left part, this I fills W is W. On the right part, actually there are two channels. W fills W, it could be I, or W fills W, it to be W. So there are two of them. That means after acting the W symmetry, it can map this soliton to an anti-soliton or to a WW particle on the W vacuums. And because this non-invertible symmetry is commute with Hamiltonian, so all the three states, they must have the same mass. And that means the particle state, they will emerge by acting the non-invertible symmetries almost for free. Actually, this structure is this ladder-like diagram, the formal algebras, which is called the strip algebras. And the horizontal lines, the symmetry line operators, and the vertical lines, they belong to some modules, or roughly speaking, just representations of the symmetry categories. And the multiplication is just defined by gluing the lower end with this upper end, and then you fuse these two L and K, you get some multiple channels. In the SSB phase, one can always set M equal to C itself. The representation of these strip algebras, it encodes all the multiple structures of between the particle and the soliton excitations. And it turns out that for SSB phase, the representation is simply C itself, the symmetry category itself. So that means the irreducible representation of the strip algebra is one-to-one correspondent to the symmetry generator. For example, if C is a Fibonacci category, there are two irreducible representations represented by this two quiver diagram. Here, each node, the node of this quiver diagram is stand for the vacuum I and W. And the arrow, this link, is the particle or solitons connecting two vacuum. For example, this connecting the identity and W, and this one is a particle in the W vacuum. So this is just the three-dimensional representation we see before. And there's actually another two-dimensional representation which is unstable actually. Okay. So that's a review of the bosonic story. Yeah.
Does the symmetry constrain the degeneracy for excitations built on top of the particle itself?
On the top of the vacuum, yes. That's right. So this tricritic Ising model again is let's motivate this fermionic story still using the tricritic Ising model because this is also endowed with supersymmetry. And it's very easy. There is this Zito symmetry eta, which can be Fermianized such that this TIM will be Fermianized to the n equal 1 A2 superminimal model with such a super-Landau-Ginzburg descriptions where this superpotential is a cubic superpotential. This capital phi is a superfield. Then we'll consider the deformations by the linear term, lambda phi. Here, depending on the sign of this lambda, it will flow to either gapless or gapped phase. And if you choose lambda to be smaller than 0, it will flow to C2 SSB phase here. And you can see that from the potentials, when you can write down the potential, it's like that. This is the bosonic part, and this is the mass of the fermion. And it's exactly like that. It's the same figures I show in the introduction. And the Zito symmetry will flip the sign of phi, and also it acts like a chiral rotation of the fermion. So these two vacuums, they differ by the mass. The mass of the fermions, which is just the expectation value of the scalar field. And you can choose one of them to be a trivial vacuum, a trivial phase. Then the other one will be a fermionic SPT phase. The soliton solution is like that. It's like this blue one. And it preserves half supersymmetry. And if you act the broken supercharge, the second part, second component, it will generate a Majorana zero mode, depicted as this red one, localized at the core of these solitons. And so now it is a good place to introduce the so-called superfusion category. We see that the C2 symmetry eta, this is actually a domain wall separating different vacuum, and it can support a Majorana zero mode. And therefore, when you draw this eta line, you can choose to decorate that with a Majorana operator or not. There are two different ways to draw this line. And then if you fuse the eta, because then there will be two Majorana operators which will span the superspace C1/1. There are two channels when you fuse eta: bosonic identity and fermionic identities. And in general, the non-operators L, they are classified as a Q type or M type, where the Q type is the non-operator like this. It can support the Majorana zero mode, but M type is not. It doesn't allow any fermionic degrees of freedom on that. And also, you can, for this fusion junction, it can also carry some fermionic degrees of freedom. That is reflected by the fusion channel. If you fuse L1 with L2, there will be, I will write this as a CNB/NF-L3, where this NB is a bosonic channel and NF is this fermionic channel. So very roughly speaking, the type of the nice operators, M type or Q type, combined with the type of these junctions and also the anomalies, which is actually encoded in the F-move, the associator, those three pieces of information will determine the superfusion categories. So let's go back to the N=1 case. Here we are assuming the non-operators or vacuum, they are still corresponding to, still one-to-one correspondent to the, they are still a correspondent between the non-operators and the vacuum in SSB phase. So the trivial vacuum is I, the minus vacuum, SPT vacuum is eta. Then let's begin with such a solitons, eta I soliton. If this eta is M type, which means there is no Majorana degrees of freedom supported on that, then it will map this eta I to simply to an anti-soliton I eta. It's like that. Then you can draw such a quiver diagram. The solitons, they are soliton, anti-soliton, they are doubly degenerated. But in the present case, eta is Q type. So it will map this soliton to a pair of anti-soliton, depending on whether you attach a red dot here. Actually, you can also think of attach a red dot at the other junctions, but since eta is a Q type, you can always move this red dot to the left. So these two are the only two independent channels. And then you can draw such a quiver diagrams. There are, for each soliton, there is a fermion and boson doublet, and also the same to the anti-solitons. There is some debate about these soliton structures, because you see in this case, the soliton has a single Majorana zero mode, and an odd number of Majorana zero modes usually cause some problems. There are actually two different viewpoints on that. The one viewpoint is the broken supersymmetry is actually map the soliton to another soliton. It's just like would be drawn here. The soliton is doubly degenerated. And another viewpoint is that the soliton is actually invariant under the broken supersymmetries. But if you impose this, then the -1 to the F is broken. So here I will not try to say which one is correct, but it seems that our analyze agree with the first one, and we will adopt this first viewpoint. And if you put the theory in a box, you may find there's a zero mode on solitons, and there's another zero mode at the boundary of the wall. So the number of zero mode is still even. So this is for the N=1. Then let's consider N=2, still a K-minimum model with these superpotentials. And it also falls to a gap phase with K+1 vacuum. For example, for A5, the potential look at that. There are 1, 2, 3, 4, 5, there are 5 vacuum. This N=2 model is due to this SU2 coset model, and with these deformations. And therefore, you can work out the symmetries in the bosonic case, in the bosonic size, and then do the fermionizations to read out the symmetry of the fermionic size. then it turns out the superfusion categories has exactly k+1 M-type line satisfying this fusion rule. And there are some, you see there are some fermionic fusion channel here. Here we also assume this Ck+1 is spontaneously broken. There are k+1 operators, which give rise to the k+1 vacuum. Then still let's consider the simplest case first, k=1. Then the superfusion category still is like a Z2, but it's not quite the Z2 well, it's a fermionic Z2, where this eta square is C0/1I or the fermionic identities. And therefore, it will, if you choose the arrow, choose the orientation of the line in this way, you see this eta, it will map a soliton to a anti-soliton and also change the statistics because of the because of the red dot here. There's a red dot here because it's eta fills eta, and depending on this fusion rule, there should be this should be Grassmann. But there's no red dot on the right-hand side because this is eta fills I. And you have such a quiver. There's a maybe there's a bosonic soliton and a fermionic anti-soliton. So here actually, this fusion category, this C2 actually it do not know about the supersymmetries. You can consider some other series with the same symmetry C2, but do not have any supersymmetries. This is totally okay. And it turns out the physical spectrum is actually 2 copies of the irreducible representation of the strip algebra. So it's still, for each soliton, anti-soliton is doubly degenerated. And also in this case, compared to N=1 case, the N=2 soliton do not suffer the problem of all the number of Majorana zero modes. Then you can move to the N=2 case where the non-invertible symmetry enters. The superfusion category is like the Ising category, but its n square is a fermionic type, is I plus eta. The coefficient is a Grassmann. Then begin with a soliton, for example, K and I. It can be mapped to the K and eta by the eta transformation through this channel, or you can act the non-invertible symmetry N, and there are 2 channels. The left one is you see the left part is N fills N to I. For the second diagram is N fills N to eta. And for both of them, you have this Majorana operator here. So this will map the soliton, Ni soliton to In solitons or eta N solitons, and it will change the statistics. And therefore, in total, we have 4 states with alternating statistics like that. And you can do this for other series, for all N=AD type minimum models. And it turns out that the results after the doubling, because of the N=2 supersymmetry, is exactly agree with the integrability results. It's showing like this. So let me conclude. So here, the non-invertible symmetry is playing an important role in the 2D gap phase, and it constrains the representation of the particle and the solitons. Here we consider the generalization to the fermionic theory and study the N=1 and N=2 minimum model. They matched with the previous results. And due to the time, I cannot show all the results in our draft, in our paper. Actually, we can also apply this non-invertible symmetry to count, like, for example, the Witten index of the supersymmetric series. It's also matched. Yes. There's one possible very interesting future directions, is that there's actually a correspondence between the 4D N=2, A1, AO, the Jia-Stockner series, with the 2D N=2 A-type minimum model, which is the model we just studied in David Tong's paper in 2006. And it turns out that the 2D vacuum is correspond to the 4D vortex, and the 2D solitons connecting different vacuum is a monopole. It's a monopole trapped in the vortex. So the question is, can we say anything about this 4D series? Is there any, so for example, non-invertible symmetry corresponding to this 2D case, to correspond this thing to this 2D non-invertible symmetry in 4D? So I think that's the end of my talk. Thank you.
All right. Questions or comments?
Can you say a bit more about the correspondence?
Oh. Here, as soon as we begin in the Jia-Stockner theory, then you consider some deformations to the Higgs branch. Then there will exist some, in Higgs branch there exists a vortex strings. And then if you consider the effective theory on that vortex string, it turns out to be this equal to A-time minimum models. And therefore there is such a correspondence. For example, these vacuums, now the 4D vortex is classified by, for example, if you pick a U1 vortex, you can embed this U1 into the different SUN diagonals. And that different vortex will correspond to the 2D vacuum. And also if you have two different type of vortex, for example, the first SU2 argument and the second SU2 arguments, in order to connecting these two, you need to have a multiple in between. And this multiple seems to related to this 2D solitions. Yes, this is some correspondence. But yeah.
And then I think question from this, I think the models, which would be describing single excitation with special radii of the modularized rays. Do these non-invertible symmetries carry over to something else?
Sorry.
Would the non-invertible symmetries carry over to such models maybe that you can use instinctively as a well, should it be?
I don't know actually. We didn't consider that model actually.
That's not the
I think
Cordova did. Cordova considered this. What the answer though? Other questions? Right. If not, let's thank the speaker again. Then